Hello and welcome back, lovely ladies and gentlemen. This is Paolo, your host, and this is another very interesting episode of Conversation in Artificial Intelligence. Today, we have a top secret scientist revealing artificial intelligence secrets. Just kidding. So today, we interview Seyed Sajjadi.
Thank you for having me today, Paolo.
So why Seyed is such an interesting character for us? Because he actually works for secret project and NASA and Boeing, but unfortunately today he's not going to talk about the secret project, but he's going to talk about project that he's working with the University of Southern California, Los Angeles, which is about broad artificial intelligence. So basically today, what you're going to learn is where the cast for human-like intelligence is going and what it is the frontier in this area. Before we go any further though, if you're new to the channel, it is an honor and privilege to have you here. If you're coming back, thank you so much for putting your trust on us. Seyed, tell us a little bit about yourself. How did you end up being a top secret scientist?
Watched a lot of Marvel movies, but jokes aside, I was always interested in intelligence. By intelligence, I'm not talking about, central intelligence agency. I'm talking about intelligence as in human intelligence and artificial intelligence. And I thought that, okay, so if I'm interested in intelligence, probably going biology or biochemistry route is the best. So then I can study neuroscience. So I went to Utah and started studying biochemistry for a little while, and then they had me open up. It was also negative 30 degrees. So after one semester, I said, no, thank you. I think this is too cold and too bloody for me. So then I left Utah and I thought, okay, so how else can I study intelligence? And then I read more about AI, and at the time I was also competing in RoboCup. So RoboCup is this community of computer scientists and a lot of other engineers. RoboCup, not the COP movie, but rather CUP. And the objective of this community is to win the best human soccer team of the planet by year 2050. Back in 2009, we won the first prize of simulating the brain of these 11 soccer agents. So I had a little bit of AI background, and I thought, okay, so let's do computers. So I came to California, went to California State University and studied computer engineering. And that's how I learned more about AI, and I got some of the jobs that are related to AI. And now I've been doing AI for more than a decade.
We see a nice surfing board here in your room. Tell us a little bit more about you enjoying life in Los Angeles. So what's going on?
Part of living in LA is the beach lifestyle that unfortunately I haven't enjoyed in 5 or 6 years, I guess. But the last time that I touched that board was probably in 2013 or so. I used to go to Huntington Beach, which is pretty close to LA, 5 a.m. in the morning. And we used to do surfing for a couple of hours. And then at 8 a.m. we would go to work. So 5 to 8 surfing, and then 8 to 5 working again. And then the cycle would repeat over and over and over until I hit a point that I realized I need more sleep, and I couldn't afford the traffic anymore in the morning. So I stopped.
That's unfortunately the reality of Los Angeles. I lived it for a while. It's nice for many things, but the traffic, it kills so many of social activities. I cannot tell how many times people were telling me, okay, I want to come, but it's too much driving. I'm not going to come. And it's kind of a killer. One thing that I find very interesting about your background is that usually people, they go out of academia and hardly they come back. It seems that you have had the pattern to work for, if I'm not wrong, for Boeing, for NASA, but you're still collaborating with academia as well. Can you tell us a little bit about how things have developed?
One thing that I realized about academia is that there is tremendous room for error. So if you're working with a professor, if you're working with a lab, even if you have a multi-million-dollar research grant, there's still a good amount of room for error that lets you experiment with different things and lets you try new things. And unfortunately, that room is not that huge when you go to industry. So in industry, okay, so maybe you can try one thing that's totally new, and there's a risk that you will fail. But then your manager or the manager of your managers are not going to be that open. Oh yeah, we have this Seyed guy that's been trying things for the past 2-3 years, and there's been zero business value. So that's why I've been kind of between the two. The things that I do in academia, like artificial general intelligence, To be honest, there's no room for it in industry yet, because industry is more focused at, higher accuracy, better performance, lower computation time. In industry, you're not necessarily too concerned about it, but rather in academia, you want to make new things that have never been tried before. You want to make improvements. And even if you fail, that's okay. It's just another research that probably won't be published, but you're not going to get fired over it. So that's why I've been going back and forth between the two.
When I met you, I learned that you were working on general artificial intelligence, and that was from my curiosity. From your viewpoint, what is the difference between artificial intelligence, machine learning, and deep learning? Because these are the three words that people hear in the media. Everybody has a different understanding of these three words. Let's define what they are.
Artificial intelligence, the whole goal of artificial intelligence that started many years ago is to create human-level intelligence, period. Machine learning, on the other end, is learning from data. So learning from data as in, let's say previously we had an AI that was playing chess, but it was not based on data. It was based on predefined rules. So developers would define rules in it based on the rules of the game of chess. You could have an artificial intelligence that would play against humans. Machine learning, the paradigm changed and said, okay, there are rules that, number one, we don't understand. Number two, even if you do understand them, it's going to take us a long time to code them and modify them and make sure that we are up to date with every single rule. So learning from data is machine learning. So we have this big bubble of AI. Machine learning is a part of it. And now deep learning is a part of machine learning. AI is the whole surface or the sphere that we can think about human level intelligence, which can be from data or not from data. Machine learning is learning from data, and deep learning is a very specific field within machine learning that uses neural networks to learn from data. That's the best that I can do at distinguishing the three.
How the three of them solve different problems. Can you give us kind of an example of three different things that are done by these three different, or superset, if you like, of human knowledge?
One of the first things that was solved in AI, or researchers tried to solve in AI, was path planning. So let's say if you have a robot or if you have a car, one thing you want to do is you have the starting position, you have the ending position, and you want to do a path planning so you can go from point A to point B. This requires zero data. All you need is the starting position, the ending position, and all the obstacles on the way. So this was done 3 decades ago, I think, a lot of Dubin's algorithm. So this is basic AI. Thousands of other examples that we can also talk about. Machine learning, on the other hand, is going to say, okay, I'm not going to use geometric formulas to solve this, but rather I'm going to have one agent that's going to try to go from point A to point B probably 1 million times, and it's going to gather data every single time that it goes from point A to point B. Let's say you can reward it whenever it gets closer to point B, and you would give it a penalty whenever it hits the wall. And then from those many iterations, it would learn that, oh, hey, if I'm getting closer to an obstacle, I want to go away from it so I won't hit it until I reach my destination. So that would be machine learning approach. And then deep learning, which is, again, within machine learning, you would be using neural networks to learn this behavior.
To somebody that doesn't know what neural networks are, what is the difference? Like in one case, you're trying many times until you learn. Basically, it's like a mouse in a cage that until he understands that has to turn. How is machine learning, let's say, different than deep learning in this case?
We're going to think about the features that are important when trying to learn a task. So we're going to talk about, let's say, 2 features. One is the speed of the agent that's trying to go from point A to point B. And the other one is the closest obstacle. I'm going to say, Paulo, if I give you these 2 things, you're going to be able to learn to get from point A to point B. And you would say, okay, Seyed, and you would go on route and you would figure out getting to obstacle is more important than my speed. But then you gain some momentum and you hit a wall and then you realize, oh, wait, maybe my speed is also important. You keep doing these iterations until you figure out the importance of each one of those features that I give you. So these are manually handed over to you, and I say distance to the wall and the speed. And then based on those, you would say, okay, I can get to my destination. Deep learning, what it does is you don't give it those features. It can learn millions of features internally. And then what it does is after many more iterations, you have no idea what features are important, but the deep learning model can mimic that behavior very accurately.
So for our audience, the difference is basically The deep learning is for certain type of projects is a little bit more intelligent. So you have to feed into the deep learning process less human intelligence. So you do not have to give hints. In the standard machine learning process that was developed at the get-go, and it's still being object of several research in many fields, the human intelligence is coded by giving hints to the algorithm, saying, look, if you want to solve this problem, look at the speed, look at the distance, look at the size of your obstacle. In the deep learning, you just give a bunch of examples, and the algorithm, theoretically, it's going to figure out how things work. But then this is kind of what the general public would understand as artificial intelligence. It would be, you just give an example, you give a problem to solve, and the machine does everything like a human being. So where is the gap between deep learning and true intelligence?
So for humans, if I learn to open a bottle of champagne, probably I can also, without any further tutorial, I can learn to open a bottle of wine, right? That is where the gap is. You can think of it, at least one of the things is generalization. So now we can train a lot of deep learning algorithms on a computer vision doing a great job at many controlled tasks where they can play Atari games, or doing very specific natural language processing where they can say, okay, I'm reading a tweet, this is a positive tweet or this is a negative tweet, from the reviews on a product, for instance. What we humans do is generalization. So once we give new tasks that the system has never seen before, then they would fail at it. That's an active area of research known as zero-shot learning or one-shot learning. And what you do in zero-shot learning or one-shot learning is exactly what I just described. So provided some different training data, we would try to learn a new thing by just looking at it once or not even looking at it. So that's one-shot versus zero-shot learning. That's one area. And then another one is all of these systems that I talked about, let's say computer vision, control, or natural language processing, each one of them would probably on its own be a different system with a different input. So one would take images as the input if you're trying to detect objects. The other one would take in your sensory data to control a system if you have an autonomous car. And then the other one is it's going to take, the speech, and it's going to convert that to the semantics that's required for it to respond. Humans, we don't have that, right? We do say this is the visual cortex and we have the prefrontal cortex and all of that, but, we are a learning system as a whole. And that's the other thing that's missing. We haven't figured out on how to join all of these different things together. How can we have an intelligent agent that can walk like a human, that can talk like a human, that can understand like a human? We're years away from that.
I think there is another element here that should come into play. And it is, in order to do the same function, the human brain uses a fraction of energy than what the GPU or a processor uses. What do you make out of that? Like, what can we infer from that?
Number one, what you're saying is absolutely true. And we are, through many years of evolution, I guess we can say that our brain and our body generally is optimized for energy consumption. I was seeing this photo of the game of Go and AlphaGo when it was solved by DeepMind a couple of years ago, and they won the best player. On one side, there was a picture of the human with 1 cup of coffee, and on the other side was AlphaGo system with hundreds of thousands of GPUs, 100 plus scientists, and a couple of years. So what you're saying is absolutely true. And energy consumption, it's not even being considered yet. Even if we can solve the intelligence problem with 256,000 CPUs, then that's something that the current research is willing to pay.
Why are we far from having a system that thinks like a human being? Can generalize. If it learns to click this pen like this, it will learn to maybe look for another pencil like this other one. So for example, we have this other one, the bottom is here, the button is here, and we understand this concept pretty quickly. The other gap is that the entirety of senses, like a vision, understanding of language, voice, understanding of information that come from different sources plus context, it's not unified yet in artificial intelligence. And what is the obstacle to do this?
I'm not sure if it's obstacle or if it's going through the natural pace that it should be going, but we're getting a lot of good results from these narrow systems, right? So we're having this amazing systems that are doing a better job in detecting objects than humans do, right? In 2012 or 13, computer vision accuracy surpassed humans. We have now natural language processing that's decent. Maybe, we haven't exactly surpassed human accuracy. We're getting close in question answering on a lot of, like Jeopardy was solved, a lot of important stuff. So we're getting good results from narrow systems, which is super interesting. And I think a lot of the research effort and financial backing definitely is going through those. So I think for that reason, we haven't spent much time on, okay, how are we going to merge all of this? Maybe the natural pace is for us to get good systems individually, narrow systems that do a one job really good. And then as that goes through, we can figure out how to merge all of them together.
Why we haven't done it yet? Where is the challenge?
I guess we don't know what intelligence is exactly. I mean, we're taking, a couple of steps at it. We think an intelligent system needs to detect objects. It needs to understand language. But the fact is, us as humans, we don't know what our intelligence is. We don't know what our consciousness is. And it's really hard to develop something that we can't even define. So I guess for that reason, that's definitely an obstacle on its own, which is why there's a whole field of neuroscience and computational neuroscience that's exactly trying to understand, okay, what are we as humans? What defines our intelligence? Are we just, a system that detects objects and can talk about them, and then we have, some control functionalities? Is that it? What else is involved? And then these go hands to hand. So if there's a new thing that comes from neuroscience that says, okay, now humans can access memory like XYZ, then people in AI do implement that understanding or new understanding of the intelligence.
That's kind of an interesting, if you like, also philosophical question. It's basically we're trying to study ourselves and clone ourselves without, we might be approaching the limit of our own cognition, basically. And that's a big question mark. But so how does all of this then feed into the research in general artificial intelligence that you do? What problems do you specifically work on?
The approach that we have in general intelligence, I'm working with, as you said, University of Southern California, USC professor. The idea behind our approach to general intelligence is we have one gigantic factor graph. And factor graph is a mathematical representation of a graph that has flow in it, right? Which is, we can think of it as our human brain. Our brain is essentially one graph, has a lot of connections, and we can learn different things. So using this cognitive architecture, you're trying to bring intelligence. So now using this one graph, trying to learn how can we identify objects, how can we have a conversation, how can we learn to move in a maze, and things like that. So joining all of them together in a single mathematical representation is the focus of our research, the cognitive architecture group.
In terms of this research, would you define it more theoretical in nature, so you look at the math of it, or it's more experimental?
There's a lot of math involved, but we do have implementation in all of this. Our code is in Lisp, which is essentially the oldest language in AI, and it's not that common anymore given all the new Python libraries, but it's in Lisp. And every new idea that we talk about in our mathematical representation, we also present it in code implementation through Lisp.
What are, let's say, some of the problems that you solve that are like an incipit of real intelligence or more close approximation of real intelligence that the deep learning of the world cannot do?
One is that unified system. We have a couple of objectives within our project. So one is sufficiently efficient. We don't want, our processing time to take forever. Functionally elegant. We want something that when we look at it, we know that this is an elegant and modular system that we can improve on. Generically cognitive. Most of the findings that we have are based on neuroscience studies and cognitive architecture studies. It's a grand unified. It's unifying all the things, the research that has been done in computer vision, in NLP, in reinforcement learning, in one grand unified system, which is why we call it Sigma. So Sigma, the mathematical representation even it sums up everything, right? You have it on the whiteboard as well. Our research on Sigma is grand unified because we're merging all of these new findings and all the good stuff that's coming from research community into a system that we know does have the potential to get to human intelligence level.
Have you created a model experiment that says, in this experiment, deep learning could not work or would work with this type of results, whereas ours is completing the task?
There are different benchmarks. One is OpenAI gym environments. So in gym environments that's created by OpenAI, you get to solve a lot of control tasks. And that's one benchmark that we have been using. So in a control task, there are a lot of Atari games. There are a lot of other simple grid world environments that you have a 2D environment and you try to go from point A to point B, and the agent has to learn that. So we've been testing it against these. On the other hand, we have some game engines using Unity that we try to have conversations between different agents, and the agent has also to walk through a maze within this game environment. More recently, we just got approved for a Army Research Lab research that's going to focus on synthetic training environments, STs. The idea behind synthetic training environment is there are a lot of scenarios that generals want to play or commanders want to play that's not feasible in reality, right? Because you can't have a war in downtown LA, but in simulation you can do all of these. And within these environments you would need human level intelligence. Our focus is going to be creating those agents that are going to be talking with other soldiers, that are going to be having their own agenda and are going to be having their own control functions from walking and all the other basic stuff, along with a lot of computer vision, of course. So that's, I think, going to be an amazing benchmark. That's just about to start. But other than that, general intelligence hasn't received much attention for a standard benchmark, which is why we have to test everything in isolated different environments, or as what we've done in the past couple of years, train it in our own internal benchmark.
Basically saying there is not really a way to compare the two 100% because usually the type of experiments done are a little bit different. But let's try to address this question in a slightly different way. Why is the Army then offering a grant to you rather than offering a grant to somebody that is doing reinforcement learning? There has to be something that they know it's not possible to do.
That one thing is grand unified. That is, if you train a reinforcement learning to have a 98% accuracy in controlling autonomous cars, that system is not going to be able to identify and recognize objects in a computer vision problem. Those are two different domains. Now you have to create a new computer vision system that does object detection. And then, okay, so now you can control a car, and then now you have to build another system that does object detection. Then you want to have conversations in this environment. That means you have to create another natural language understanding system that does this for you, right? So these are the whole reason behind our Sigma model is it's one grand unified system that can handle all of these together. So we do have the potential of learning control tasks within the same system, within the same graph. We can also teach the agent to recognize different objects of interest. They can also teach the agents to have an intelligent conversation with another intelligent entity.
If you look at this contract from the Army Research Lab, this is an initial application of this broader context of artificial intelligence.
Absolutely.
When do you think we will see more applications of this? Do you think they're for now restricted to the realm of military and defense, or you think there's going to be other areas where we can see some of these applications?
The reality of it is usually government research agencies are a couple of steps ahead in investing in research that doesn't necessarily have an immediate business return or a return on investment. And it does make sense because you want the government's research agencies to make one thing possible, an idea possible, and then they would hand it over to industry, where in industry people can make that mainstream. The place that I think general intelligence can be mainstreamed is through personal assistance systems. So currently you have, let's say, Siri, you have Cortana, you have Alexa, you have Google, all these different systems that are getting some initial understanding of the conversation, but they're still not unified in a sense that they essentially are just running a fancy Google search in the background. But if you can have a general intelligence that understands your personality and your needs and your character, then I think that would be the first place that the mainstream market and industry would be highly interested to invest.
In your own opinion, the research that is being done today in your lab or other ones, how far is from application? So if basically we took it today and we put it inside Alexa, would we get better results or would we get worse results?
You won't get more accurate result per task, but you'd be able to cover more tasks and a broader range of tasks. How long is that system away from achieving satisfactory results? I would say couple of decades.
Do you think that the fact that these large companies are not investing right now in this type of technology is obstacle to the speed with which this technology can develop? Like if I have 10 Seyeds or I have 100 Seyeds doing this, would I speed it up to 20 years?
It would, yes. The general intelligence community is not receiving that much love because, again, all the other more specific, narrowed applications are achieving superhuman accuracy performance. And that's really interesting from research standpoint and from investment standpoint. A couple of decades away, there are very few companies that are interested in this. So OpenAI's idea is specifically about general intelligence. So OpenAI was backed up also by Elon Musk, and their vision is also to take all the current state-of-the-art applications of AI and machine learning to a state where we can have human-level intelligence. DeepMind is also doing a tremendous job in moving the research forward in these fields. Again, I think it's going through the natural pace, and getting good results from these narrow applications is a little bit more interesting than maybe building a system that would potentially get to human level intelligence, but we currently do not have a business model for it. So it won't be sustainable in a mainstream market.
I could think a lot of things that would make $1 billion with the general intelligence system. By the way, the other thing I think is interesting looking into in this realm of the future. I know this might be kind of a surprise question, but there is another field that is more connected to the physical research that is coming up, and that's the field of quantum computing. And so giving computers an entirely new realm of logic to work on. What is needed to reach human level intelligence is kind of a more powerful computers or more powerful math. If we have the quantum computers combined with your research, we get better results, or the problem is somewhere else?
The problem is three things. Number one is definitely computational power. Now, there are a lot of things that are being done on CPUs, GPUs, and now TPUs for TensorFlow. Then quantum computing can be the next step in speeding things up tremendously. So definitely computational power is one bottleneck. The other one is the algorithms, or you refer to them as the math. So the algorithms behind how we go through a lot of data and how we go about a learning algorithm is highly important. And the third one is the data. Behind the explosion of machine learning and deep learning in the last decade has been the marriage between the three. So we got access to more powerful computers, better algorithms. However, you can argue that algorithms were there already from the late 90s, as well as the data. So if we keep improving on these three, then I think we're on the right path on getting to general intelligence within the next couple of decades.
It looks like for everybody that is watching on this, looks like the time that we get to hold the famous computer of 2001 or this Space Odyssey seems a little bit far. I was hoping to hear that next 5 years we're gonna get the kind of intelligence. But on the other hand, it's interesting to know that government research agencies are pioneering these new fields. And it's only 2005 when the DARPA invested in the autonomous vehicle. And now a little bit over a decade after this entire research, now it's really going into mainstream industry. And there is no one car manufacturer that doesn't have an autonomous driving program. Although Seyed said it's 20 years ahead, we never know. Some instance of this research will probably see the light of some specialized applications in the military in the next 5 years. And then in the next 10 to 15 years, the industry will start talking about it. And somewhere down the road, it's going to be adopted. With that said, thank you, Seyed, for being here today.
Thank you for having me today, Paolo. This was a pleasure. I loved our conversations and looking forward to some good results from general intelligence community. And I hope it does happen sooner than what I anticipated.